We see them everywhere. We use them in our television sets. We also see them in our Ethernet connections. And we also see them being used in subscription televisions. We present coaxial lines. Coaxial lines or cable consist of an inner conductor surrounded by a flexible braided conductor, usually copper, with the two being separated by a dielectric. The information is being carried or transmitted by the center conductor, while the surrounding layers prevent attenuation loss and help reduce electromagnetic interference. Here we can see a set of coaxial lines of varying sizes, and there is a specific application for each of those. RG11 is used with thick Ethernet, RG58 is used with thin Ethernet, RG59 is used with cable television, RG62 is used with ArcNet, and RG174 is used with cellular communications. Coaxial cable is commonly used for noisy locations and high-frequency applications. Among its advantages are the following. It does not radiate energy to the complete shielding. As we have shown in the previous slides, the coaxial line or cable is completely or thoroughly surrounded by a dielectric, and it is further surrounded by a braiding of conductor, which means it is completely sealed, and with that, energy cannot be radiated outwards. And also because of the same reason, it is noise resistant, because if energy cannot come out of the wire, thus energy cannot also come in. It is also noise resistant, and it works up to 18 GHz. Among its disadvantages are the following. Common mode current occurs when the stray currents in the shield flow along the direction of the current in the center conductor, causing the coax to radiate. And a small continuous current along the shield can cause visible or audible interference. Here we can see the data of standard coaxial lines. The two most common types of coaxial lines are RG58 and RG174, and that they have the same characteristic impedance of 50 plus or minus 2. We can also see here that RG58 is larger in diameter as compared to RG174. This is because a higher number in a coaxial line indicates a thinner wire. And the velocity of propagation in RG58 is 67% of the speed of light, while RG174 is 66% of the speed of light. That's a minor increase in speed in RG58, and their capacitance are almost the same, 101 for RG58 and 100 picofarads for RG174. Their attenuation for RG58 is 170 decibels per kilometer, and for RG174 it is 300 decibels per kilometer. Now, this experiment number 2, requires us to perform measurements on coaxial lines regarding its various parameters. Such a procedure requires us to use a bridge meter that is only available in physical laboratories. However, due to current circumstances, we cannot afford to perform this experiment in a physical laboratory. As such, we will only base our data in sample plus data that is provided to us, and we will interpolate those results over a range of frequencies. And for that, we will use Microsoft Excel. For experiment number 2, there are a total of 4 tables, which we will be discussing individually. To start off, let us discuss the table number 3.
So we can see on table 3 is the resistance and inductance values for both 100-meter cable sections for RG174 and RG58 from 20 Hz to 300. As we can see, with increasing frequency, the measured resistance of the line is also increases as well, meaning that the relationship that exists between them is that they are directly proportional to each other. For lower frequencies, the resistance is small, but at higher frequencies, the resistance of the cable becomes high and significant. The frequency and the inductance are inversely proportional to each other. So to summarize this table, for RG174 coaxial cable, resistance is directly proportional to the frequency, while the inductance is independent from frequency. On the other hand, for an RG58 coaxial cable, the resistance is also directly proportional to the frequency, but the inductance is inversely proportional to the frequency.
For Table 4 is about the line quantities for the coaxial cable. This shows the values of the resistance, inductance, and capacitance of a coaxial cable given that the cable is a 1 kilometer length. This focuses on showing and comparing the two coaxial cables and see the values of the resistances, inductances, and capacitances for a 1 kilometer line. So table 4 shows that the RG174 has a resistance value of 50, the RG58 has a resistance value of 80. Meaning for a 1 kilometer line, the RG58 has a higher resistance value. For the inductance, the RG174 has a inductance of 40 microhenries, and the RG58 has an inductance of 50 microhenries, meaning that the RG58 coaxial line has a higher inductance for a longer line. And for the capacitance, the RG174 has a capacitance of 1000 nanofarads, and the RG58 has a capacitance of also 1000 nanofarads, meaning that the capacitance remain constant even at a long cable. For
Table number 5 is about the phase duration and the phase velocity of coaxial lines, specifically RG174 and RG58, when exposed to varying pulse durations. For a 50-meter RG174 coaxial line, the the phase duration is 456 nanoseconds, and for 100 meters, it is 944 nanoseconds. For 50 meters RG58, it is 496 nanoseconds, and for 100 meter, it is 900 nanoseconds. Now, the phase velocity of an RG174 is 71% of the speed of light. Meanwhile, the RG58 is 69% of the speed of light. And it is noticeable enough that signals travel through RG174 a little bit faster than it does in RG58. And we can also see that the parameters of coaxial lines are independent of the pulse duration. You can see in this plot that for a 50-meter coaxial line, the phase duration of an RG58 is higher than that of RG174, and otherwise it holds true for 100 meter. Now let us discuss table number 6.
The fourth and last part of the experiment is about the power transmission with the coaxial cables. We have observed the transmitted power as a function of the line termination Z2. According to the table 6, the line power is maximum at 120 ohms, since the ratio between P2 and Pmax is equal to 1 at this resistance. Also, the voltage U2 is at maximum value at 120 ohms. This resistance may also be the characteristic impedance of the line, hence, maximum power transfer occurs. However, based on the info on table number 1, the characteristic impedance for an RG58 coax cable is around 50 ohms. The prior assumption may be wrong. On the plot of R2 versus U2, P2, and Pmax, we can easily spot that the tip of the spike is where the line power is
Presented here are various factors that affect or contribute to the attenuation of a coaxial line. First, we have length. As we know, the longer a wire is, the greater its attenuation will be, as provided by the equation of resistance, that is R equals rho L over A. And frequency. The higher the frequency is, the more it triggers the skin effect, which causes attenuation. Other losses also include resistive losses, dielectric losses, and radiated losses. Also, other factors include flexing, braid contamination, moisture, and degradation of braid. And here are some important equations to note about coaxial lines. And that's pretty much it. That concludes our report for experiment number 2. And here are our references. Thank you for listening.